Chemistry Quarter 3 Assessment Review. You can access this video and this review at srhschem.wikispaces.com. First section is on stoichiometry. Butane reacts with oxygen according to the reaction given below. First question is asking for the mole ratio between butane and oxygen. So if we look in the chemical equation, butane is C4H10, and there are 2 moles of that. And for every 2 moles of my butane, I have 13 moles of O2. I can also write this mole ratio by flipping them for 13 moles of O2 for every 2 moles of butane. Mole ratio is always between moles, and they come from a balanced chemical equation. So how many moles of butane are needed to fully react with 26 moles of O2? So we're going to start with 26 moles of O2 over 1. And I want to cancel out mole of O2, so that will go on bottom. And I need to solve for moles of butane. So at this point, if I solve, my answer will be in units of moles of butane. So we're done. So all that we need is our mole ratio. There are 2 moles of butane for every 13 moles of oxygen. So we can solve, and we get 4 moles of butane. You could also solve this problem if you realize that 26 is exactly twice 13, which is the number of moles of oxygen in the balanced equation. So if I need 2 moles of butane for 13 moles of oxygen, if I had twice as much oxygen, I would need twice as much butane. Either way, we get 4 moles of butane. Next question, how many moles of oxygen would be needed to react with 10 grams of butane? So we'll start with our 10 grams of butane, C4H10. And in my chemical equation, everything is in moles. So if I want to go from butane to oxygen, the way to do that is using the mole. So first I'm going to need to convert grams of butane into moles of butane. So this is going to require the molar mass. At this point, all that I've done is just a quick conversion from gram to mole. I want to get from moles of butane then into moles of oxygen. And then I know I'm done because the question asks for moles of oxygen. So we can start filling in some of these blanks. First one is molar mass. So the molar mass of butane, 1 mole weighs 58.12 grams. So that's the molar mass. My next conversion factor is the mole ratio of oxygen, which is 13 moles of oxygen for every 2 moles of butane. So we can plug everything in, solve, and we get 1.12 moles of oxygen. Next question is asking what mass of water could be attained from burning 15 grams of butane. So I'm solving for mass of water. I want to get to grams of water. I'm starting with 15 grams of butane. So just like before, if I want to get from butane to water, the way to do that is using a mole ratio. So I need to change these 15 grams of butane into moles of butane. Once I'm in moles of butane, I can use a mole ratio to get to moles of water. And if I asked for moles of water, then I would be done. But I asked for the mass of water. So I'm going to need one more conversion factor to get from moles of water to grams of water. So now we're all set up. This will give me grams of water as my answer, so we can go fill in some numbers. So my first conversion factor is moles and grams of butane. So we're going to use that molar mass for butane one more time. 1 mole of butane weighs 58.12 grams. Molar mass, anytime you see the word molar, it always means per 1 mole. So molar mass by definition is how many grams does 1 mole of that compound weigh. My next conversion factor has mole of water over mole of butane. So that's a mole ratio. Mole ratio comes from the balanced equation. So in my balanced equation, there are 10 moles of water for every 2 moles of butane. So if I solved right now, my answer would be in moles of water, but I want grams of water. So I'm going to need to find the molar mass of water, which is going to be about 18.02 grams per 1 mole. So now if I solve, I get 23.25 grams of water. Next question asks how many liters of carbon dioxide are produced from 6.5 moles of O2. So carbon dioxide is a gas, and we usually measure gases using volume, using liters. So we're going to start with our 6.5 moles of oxygen, and I'm already in moles. So that means my next step, I can use a mole ratio to convert from moles of oxygen to moles of carbon dioxide. At this point, if I solved, my answer would be in moles of carbon dioxide. I don't want moles of carbon dioxide. I want liters of carbon dioxide. So I'm going to need one more conversion factor. So my first conversion factor is moles of carbon dioxide over moles of oxygen. So there are 8 moles of carbon dioxide for every 13 moles of oxygen. And for my next conversion factor, I've got liters of CO2 over moles of CO2. So that's one of our conversion factors. 1 mole of any gas is going to take up 22.4 liters of volume. So I can plug this all in and solve, and I get 89.6 liters of CO2. The next section focuses on solutions and the properties of solutions. So provide an example of a solution, a suspension, and a colloid. So solution, suspension, colloids are different types of mixtures. Solutions are going to be homogeneous, whereas colloids and suspensions are heterogeneous. What that means, if you zoomed in on a solution, you would see that the ions or the atoms are very evenly distributed throughout the solvent. So we would see that that was very homogeneous, evenly distributed. For the colloid and the suspension, we're not going to see everything distributed so evenly. So that's going to be heterogeneous. Solution particles are going to be really, really small. So these are going to be individual atoms or ions. So this would be kind of like if we were looking at some macroscopic objects, it would be relatively like the size of a marble, whereas a colloid particle would be like the size of a baseball. So these are going to be larger. It's going to be big molecules. And for suspension, those are going to be even bigger. So that would be like very large aggregates of molecules. So relatively speaking, if a solution is a marble, a solution particle is a marble, a suspension particle would be a basketball. So that just gives you an idea of the relative size of these particles. And if you understand the size of the particles, then you can understand all of the different properties of solution suspensions and colloids. So the first one is passed through a fine membrane. So a fine membrane is just like a filter or like a colander, something that won't let everything pass through. So sort of like whenever you pour out some pasta with some water, the colander catches the pasta, but the water flows through. But for a fine membrane, the holes are really small. So the holes are very, very small, but solution particles are even smaller, so they're able to pass through. Colloid and suspension particles are a bit larger, so those would be caught by the fine membrane and would be unable to pass through. So if you were trying to separate out the parts of a colloid or a suspension, you could use a fine membrane to do that. The filter is exactly like the fine membrane, except the holes are a bit bigger, which means that more things are going to be able to pass through. So since the solution was small enough to pass through the fine membrane holes, it's still going to be small enough to pass through the filter holes. For colloids, those particles are still bigger than solution particles, but they're also small enough to be able to pass through the filter holes because the filter holes are a bit larger. But in the case of a suspension, those particles are still too big. They're not going to fit through those holes. So they would be caught by the filter. For settling over time, again, this is based on the size of the particles. If you think about a solution and a colloid, those particles are relatively small compared to the suspension particles. What that basically means is that the water is able to hold those particles up and they're not going to sink to the bottom because the water is able to hold them up. So that's true for solution and colloid. But for suspension, those particles are so large that they just sink to the bottom. They're too big and heavy for the water column to support them. Next, the Tyndall effect. So the Tyndall effect is the scattering of visible light by particles. And the larger the particles, the more light they'll scatter. So you've seen this maybe like on a foggy day, you're able to see like a beam of sunshine traveling through fog, or maybe in like a smoky room, you're able to see the actual path that a beam of light takes. That's because whenever you have smoke or fog, those particles are big enough that they're able to scatter light, so you're actually able to see the path of the light. So again, this is based on size. For my solution particles, those particles are so small that they're not going to scatter enough light for you to be able to see the path of a beam of light. But in the case of our colloid and suspension, those particles are large enough that we're going to see light scattered. So here's an example of each one. A solution would be kind of like if you just took a sugar cube and dissolved it in the glass of water. So that sugar cube, it appears to disappear. It's not that it's disappearing, it's just that those individual sugar molecules have become solvated. They've dissolved into the water. An example of a colloid would be milk. So milk is mostly water, but it's got a lot of different molecules in it that aren't distributed evenly, that are not homogeneously distributed. So you've got sugars and fats and all kinds of different molecules that are kind of spread throughout. So milk is going to be our example of a colloid. And my example of a suspension is going to be muddy water. So if you think about muddy water, you know that it settles. The particles are large enough, like you can visibly see them. So this matches my description of suspension. Question 3, how many moles of NaCl are required to make a 1/4 liter of half-molar solution? So you need to remember the molarity equation. Molarity is equal to moles of solute divided by liters of solution. So whenever I'm making a salt solution, it's going to be the moles of the salt divided by the liters of the solution. So I want to make a half-molar solution, and I want to make 0.25 liters. And the question asks for moles. So I'm solving for moles of NaCl. So in order to do that, I got to cancel out this 1/4 liter. I do that by multiplying both sides by 0.25 liters. So on this side, it will cancel out. So I'm basically left with moles of NaCl is equal to 0.50 times 0.25. And I can solve that, and that gives me 0.125 moles of NaCl. So if I wanted to make this solution, I'd need to get together 0.125 moles of NaCl and a 1/4 liter of water and mix them together. The next question, 3 liters of solution are prepared using 9 moles of NaOH. What is the molarity of the solution? So once again, we're going to use our molarity equation, but this time we're solving for molarity. So we need to know the moles of solute, which is going to be 9 moles, and we need to know the volume of the solution, which is 3. So 9 divided by 3 means that my molarity of the NaOH solution is 3 molar. Next question, how many milliliters of 12 molar HCl are needed to prepare 100 milliliters of 2 molar HCl? So this is something that you have to do in a lab all the time. 12 molar HCl is very concentrated, and it's actually pretty dangerous to handle. So what we'd like to do is dilute that down. We'd like it to be less concentrated. Why would we even buy 12 molar HCl? Well, because it's cheaper. It's cheaper for me to have a couple of liters of 12 molar scent and then for me to dilute it than it is for me to buy the diluted stuff. So you're going to use M1V1 equals M2V2 to solve this problem. So the question says how many milliliters of 12 molar HCl? So that's going to be my M1 and V1. And the 100 milliliters and 2 molar is going to be my M2 and V2. So I'm solving here for V1, which means I got to get rid of that 12 molar. So the way I do that, since it's multiplied, I do the opposite. I do division. So I'm going to divide both sides by that 12 molar. It'll cancel out over here. So I'm left with V1 is equal to 2 molar times 100 milliliters divided by 12 molar. So I can plug this all in and solve 200 over 12, and I get 16.67 milliliters of 12 molar HCl. So what I would need to do, I would need to measure out that 16.67 milliliters of that 12 molar HCl, and then I would need to add distilled water until my total volume was 100 milliliters. Provide an example of strong, weak, and non-electrolytes. So the difference between strong and weak has to do with how much it dissociates in water. Non-electrolytes, they're either going to not dissociate, they don't dissolve, or when it does dissolve, it doesn't contain any ions that are able to carry the electric current. So in my first beaker, I've got a strong electrolyte. So I added this solute, and this could be, anything. I added it, and you can see that all of them have broken apart into cations and anions. So it's dissociated 100%. There's lots of ions there that are going to be able to carry an electric current. So it will be a strong electrolyte. My next one, if I have a weak electrolyte. So if you look in this beaker, you see that a couple of them have broken apart to give me ions, but most of them stayed together. They didn't dissociate. So I didn't form as many ions, so I'm not going to be able to conduct as much electrical current. And in the last example, this is a non-electrolyte. So whenever I added this in, it didn't dissociate. There are no ions present, so there's going to be nothing there to carry the electric current. So an example of strong electrolytes, these are going to be ionic compounds like sodium chloride or potassium sulfate, and our strong acids such as hydrochloric acid. My weak electrolytes are usually my weak acids such as acetic acid. And non-electrolytes are generally going to be hydrocarbons, so alcohols, sugars, those type of compounds are going to not conduct any electricity. It's important to note that absolutely pure water, that contains no ions. So pure water does not conduct electricity. It is only by the addition of something that produces ions when added to the water that we're able to conduct an electric current. Number 7 is to define some different types of solution. So we have saturated, unsaturated, and supersaturated. So an unsaturated solution would still dissolve additional solute if I added it. So if you think about a glass of water, and if you put a teaspoon of sugar into it, you could still obviously dissolve more sugar. At that point, we would call that an unsaturated solution. Now, if I kept adding sugar to my glass of water, eventually I'm going to get to a point where I can't get any more sugar to dissolve. As much sugar as possible has been dissolved in the water. So that's a saturated solution. These are solutions that contain as much solute as is possible under normal conditions. So if I added more sugar, even if I stirred, I wouldn't be able to get it to dissolve. So a supersaturated solution, I kind of have to do something funny to that glass of sugar water in order to get more sugar to dissolve. So supersaturated solution is a solution that exceeds its predicted solubility at a certain temperature and pressure. So it's got more sugar than normally should be able to dissolve. So the best way to do that is to take your solute, like take our sugar, and grind it up into a fine powder, and then heat the solution to help make it dissolve. Then, when the solution cools, as long as it is undisturbed, that sugar will stay dissolved even though it really shouldn't be able to at that given temperature. Draw a picture that shows the interaction between water molecules and NaCl. So here's some solid sodium chloride, and I want to point out that it's made of sodium cations and chloride anions, and these are stuck together because we are a solid. Whenever I add this to water, it becomes aqueous. Those individual ions are no longer going to be stuck together, so they spread out in the water. The other thing that's important to point out is that this is all based on charge. So in your water molecules, you've got one end that's partially positive and one end that's partially negative. We indicate that using the delta symbols. So those delta symbols tell me that the oxygen end of the water is partially negative, whereas the hydrogen end is partially positive. The sodium cation is positive. So the negative end of water, the oxygen end of water, is going to be attracted to it. In the case of my anion, my chloride, that's negative. So the positive part of water is going to be attracted to it. The hydrogen will be. So we see that these water molecules, as the NaCl dissolves, it becomes solvated. These sodium and chloride ions are surrounded by molecules. That's the definition of solvated. So, and that surrounding occurs based on charge of the ion and of the water molecule. Number 9 is about the solubility curves. So a solubility curve shows me the solubility of different compounds as we increase the temperature. So the solubility is in grams of solute per 100 grams of water. So what this means is that if I had 100 grams of water at a certain temperature, how much of these different compounds can I dissolve? So the first question asks which compound's solubility decreases the most as the temperature increases from 50 to 70. So I've highlighted 50 to 70 on my solubility curve. And I'm looking for which compound solubility decreases. So on my solubility curve, all of the solid lines represent solids. You can see that for most of those, as the temperature increases, the solubility increases. I'm looking for solubility decreasing, which means that I'm going to need to look at the gases, which are the dotted lines. So if I look at the gases, there's 3 on there. I want to know which one is decreasing the most. So I'm really looking for the steepest negative slope. So of my choices, HCl, NH3, and SO2, NH3 has the steepest slope. So that's going to be the fastest decrease in solubility in that temperature range. Next question, 100 grams of water are saturated with potassium nitrate at 60 degrees Celsius. If the solution cools to 10 degrees Celsius, how much solid potassium nitrate will precipitate? So first we need to find potassium nitrate. So I've marked it with this blue line. And I want to see what its solubility is first at 60 degrees Celsius. So that's about 110 grams. So if I had 100 grams of water at 60 degrees Celsius, I can add 110 grams of potassium nitrate and it will dissolve. Now let's see what our solubility is at 10. So at 10 degrees, I can only dissolve 20 grams. So if I had 100 grams of water at 10 degrees Celsius, I could dissolve 20 grams of potassium nitrate. So at 60, I can hold 110, and at 10, I can only hold 20, which means that 90 grams of solid KNO will precipitate into the bottom of the beaker. The solution can't hold that 90 grams once it's been cooled down to 10 degrees Celsius. Sketch a graph that shows the relationship between solubility and temperature for most solids. So for most solids, as temperature increases, solubility increases. And you know that. If you want to make sweet tea, you know that you want to dissolve the sugar when the tea is hot because it's going to dissolve better. So we see a direct relationship, a positive slope. These are all ways of saying that as temperature increases, so does the solubility. Next section is on thermodynamics. Consider the enthalpy diagram. What is the heat of reaction, the delta H for this reaction? So to find delta H, I need to look at the difference between reactants and products. So I start my curve with my reactants and I end the curve with my products. So the difference between those is going to be delta H. So I labeled this on my graph. It's the difference between 150 and 50. This is going to be a negative 100 kilojoules because this reaction is exothermic. I know that it is exothermic because my reactants start at a higher potential energy than my products, meaning that in order for my reactants to become products, I need to give off that heat. What is the activation energy for this reactant? So you can think of this potential energy curve as kind of like a roller coaster. You start at the bottom of the roller coaster as your reactants. And you know that whenever you get on a roller coaster, the machine has to take the roller coaster up to the top of the hill. Once you get to the top of the hill, you can ride the roller coaster, fall down, and become reactants. But I have to add energy to get to the top of that hill. So reactants to the top of the hill is going to be our activation energy. So for us, the reactants are at 150 and the top of the hill is at 200. So to get to the top of that hill, I need to absorb 50 kilojoules. So this will always be positive. This part of the reaction is endothermic. Compare the stabilities of the products and the reactants. So you need to know that higher energy is less stable. So between reactants and products, whichever one is higher energy is going to be less stable. So the reactants are less stable than the products because they are higher energy. Provide an example of a phase change that is endothermic and a phase change that is exothermic. So endo means heat goes in. So any phase change where the substance needs to absorb heat. So this would be melting. If I want to take a solid and melt it into a liquid, that substance needs to absorb heat. Or boiling. If I want to change a liquid into a gas, I need to add heat to accomplish that. Exo sounds like exit. So this is any phase change where heat is released or the substance is cooling. So if I want to freeze something, if I want to go from liquid to solid, I need to remove heat. That's what your freezer does. It removes heat. You can feel it at the bottom of your refrigerator. You can feel that it's warm because that's the heat that the freezer or refrigerator has taken out of your food. Condensing. So if I go from a gas to a liquid, you've seen this on the outside of a can of soda. There's water vapor in the air, and when it collides with the outside of the soda can, suddenly it cools down, and that causes it to condense into a liquid. Consider the reaction below. So the delta H for this reaction is going to be positive 67.8 kilojoules. And I know it's going to be positive because heat is a reactant. So this reaction is endothermic. Heat is a reactant. I have to absorb heat for this reaction to occur, so delta H will be positive. How many grams of nitrogen are required to absorb 156 kilojoules of energy? So in my balanced chemical equation, everything is in moles or the heat is in kilojoules, which means that I can use this balanced equation to easily convert between kilojoules and moles of nitrogen. If I asked for moles of nitrogen, we'd be done, but I asked for grams, so that means we have one more step using the molar mass. So first I want to convert kilojoules into moles. And if I look in my balanced equation, I see that there's 1 mole of nitrogen. For every 1 mole of nitrogen, I have to absorb 67.8 kilojoules. Next, I have grams and moles of nitrogen, which means molar mass. So the molar mass of nitrogen, 1 mole weighs 28.01 grams. So in order to absorb that 156 kilojoules of energy, I need 64.46 grams of nitrogen. Entropy is a measure of the disorder of a system. So for each of the following, determine if the disorder of the system is increasing or decreasing. So I included on this slide a heating curve. This is the heating curve of water, and this shows you the different phases. So if you look at the solid, it's a very orderly solid. Those particles are all held in place. They're very neatly arranged in rows and columns. So that would have very little disorder. As a gas, those particles are freely moving. They're able to fly around. There are many possible arrangements of those particles. So that would be very high disorder. So if I have ice melting into a liquid, that's going to be an increase in the disorder. So I go from that orderly solid ice to fluid moving liquid particles. Methane crystallizing into a solid. So that's going from a gas to a solid. So that would be a decrease in the disorder in the entropy. Solid iodine subliming into a gas. So that is going to be an increase in the disorder. I go from a solid to a gas. If water condenses, so I start with a gas and it ends up as a liquid. So that would be a decrease in the disorder of the system. Consider the pictures below. So in my first picture, I've got 2 blocks, and one is at 100 degrees Celsius and one is at 200 degrees Celsius. So heat always flows from warmer to cooler. So heat will flow from the 200 degrees Celsius to the 100 degrees Celsius block until they're both at the same temperature. At that point, heat exchange still occurs. It's just that it occurs equally in each direction. So they maintain the same temperature. For my water and my ice, the water is warmer than the ice. We know that because the ice is frozen. It's below the freezing point, and the water's not. So the ice is going to absorb heat from the water. This means that the ice is going to melt, but since your water is losing heat, it's also going to cool your water down. And this will again continue until they're both at the same temperature. In the reaction, oxygen plus energy, we're going to form an oxygen atom and another oxygen atom. So obviously, if I start with an oxygen molecule and I end with oxygen atoms, that means that that bond is being broken. And energy is a reactant, which means that energy is absorbed. Let's label the heating curve. So the first part of my graph is going to be a solid. Then between C and D, we have our liquid. And between E and F, we have our gas. So the flat parts of this graph are going to be my phase changes. So my first flat part is my melting point and my freezing point. So that temperature is the same. So for example, for water, the freezing point and melting point is 0 degrees Celsius. The only difference is if we are at 0 degrees and we're adding heat, that means that we're melting. If we're at 0 degrees and we are removing heat, that means that we're freezing. My second plateau is the conversion of liquid to gas. So that's the boiling and condensation point. Those are the same temperature. The only difference being, are we adding heat or are we removing heat? So phase changes occur any place where the graph is flat. This means that the temperature is constant during a phase change. Based on the data, what is the melting point and boiling point? So the melting point is going to occur at the first plateau, at the first flat part of my graph. So according to my data, that occurs at 5 degrees Celsius. My boiling point happens at the second flat part of my graph, which according to the data is 60 degrees Celsius. So which segment of the graph has the most kinetic energy and the least kinetic energy? So the most is going to occur as a gas. So those particles are moving around really fast. They have the highest temperature. They're going to have the highest kinetic energy. The least is going to be our solid. So those particles are just stuck in place. They're just vibrating in place, and they have the lowest temperature. So that's going to be the least kinetic energy. Explain why the temperature remains constant during a phase change. So in the case of my heating curve, when I get to a phase change, I'm still adding heat. It's still being heated, but the temperature is remaining constant. So that means that heat must be doing something else instead of raising the temperature. So the added heat is instead being used to break apart the intermolecular attractions that are holding the substance together in a given phase. So if I have a solid, there are very strong attractions that are holding those particles together as a solid. I need to weaken those attractions. I need to break up those attractions in order for my solid to melt into a liquid.